All right, we'll get started. We'll see how this goes. I'm the final boss between you and lunch today. I asked ChatGPT to make me a slide deck. I haven't verified any of this. I'm just kidding. That would be exciting, though. This is the introduction to satellite link security standards with CryptoLib. Before we get started, how many people actually have experience working with space-related domain and like space networking at all? Anybody? Okay, I know there's cool, and I know there's a few people here that just refuse to raise their hands because I know them. So that's helpful. And on top of that, so we got a handful of people in the room that have worked with space systems, and probably only a subset of that have actually worked with the protocols and the bits and bytes and how that works. And it's a little different than traditional networking. So that's what we're going to cover. Do some background, talk about CryptoLib, how it solves a few problems. A little bit about me. I am from Buchanan, West Virginia. In my spare time, I like to backpack. I've got about 5,000 miles and counting, none recent. LinkedIn up there. I have my BS in Math Computer Science from West Virginia Wesleyan College and my Master's from WVU in Electrical Engineering with an additional certificate for computer forensics. Obviously, disclaimer, my views and opinions may not be my employer's. All right, so absolve myself about a little bit of guilt. I work for TMC Technologies. Generally speaking, we have a few different government contract vehicles and we have a few specialty teams. The team I work on and work with, primarily we are experts in hardware, simulation, and emulation. The reason we do that is we want to test satellite binaries at the highest fidelity we can on a simulator. So the goal is that we do not cross-compile these binaries. The binary as we fly it is the same binary we're running in a simulator. It thinks it's running on an actual satellite in space. So we can test the binary to full fidelity. And if you're wondering what that process looks like, it's kind of like hitting your head off a wall because you just model something until flight software breaks, and then you have to figure out what broke, and then you model the next piece until it's happy. And then we keep going, and we, depending on the fidelity of sim, we will model subsystems, sensors, dynamics data, physics, avionics. But the whole goal of what we do is we're going to take an entire system like James Webb and condense that down to where it runs on a laptop. Depending on the level of fidelity, sometimes you're pushing it with a laptop, all right? I'm going to be honest. But generally speaking, our sims can get faster than real time. We can do day in the life, what might take a 24-hour simulation. We can do it in about 8, depending on the sim, 8 hours. And then some sims we can actually run a lot faster. It depends on the fidelity and what we're trying to achieve. So with that background, how do we get where we are now? Space data links. How do they work? We're here, satellites are not, they're up there. How do we talk to them, right? So if we just want to simplify it, we could just imagine that when they launch a satellite, there's an Ethernet cable plugged into your laptop and there's a big spool of wire, all like a harpoon gun, and the satellite goes up, and your cable, your RJ11, your dial-up line, right, is going up to the satellite. We're going to simplify this and say it's in a geosynchronous orbit, so we don't have to worry about cable wrap around the Earth, right? Because low Earth orbit, your satellites are moving about 17,000 miles per hour around the Earth. So we've got a single cable. That's how we talk to our satellite. With this cable, we've got a user, and the user says, I need to send a command to a satellite. I've got this command, I need to get it up this cable. They send the command. It goes out of a dish. I hate to break the idea early here, but it's not actually a cable, right? It's an RF or an optical link. The satellite's going to receive that command, do some validations, look at some checksums, make sure everything's A-OK before it does it, and then it fires the lasers, or whatever it does. It doesn't really matter. Probably something a little more innocuous, I would imagine. In these two scenarios, though, which is hypothetically more secure? Now, if you take the diagrams at face value, how they are drawn, they're pretty equivalent, really. I mean, what's the difference in stretching a big cable to a satellite other than it's feasibly impossible, and having a single RF link to a satellite? There's not much difference. But obviously, the real world's a little more complicated, right? In this diagram, what we've done is we've upgraded you to Cat 6. We still ignore the whole issue. And now you've got one satellite in the sky that you're talking to. If you notice, though, the radio waves from the ground are expanding, right? You know, this is where we start getting into this problem of cable versus RF or optical. So now let's think about what's up there. On the ground, you'll see I've added more users, but I've purposely not tied them into this diagram. Space, we have some more satellites. Color's not indicative of any particular nations, plural. And something that is similar to, but distinctly dissimilar from a generic off-brand F-star. So there's a lot of stuff up there now, right? There didn't used to be. We used to have significant barriers to entry, right? Everybody's heard security through obscurity. That's basically how space has operated for a long time. It's changing, obviously. But what were those barriers? It's not a single barrier, right? It's a host of barriers. There's really a few parts here. First is affordable launches. We've all heard of SpaceX, right? If you haven't, you live under a rock, I presume, or you just assume that you see a lot of comets launching from Earth if you live near a launch site. I don't know. But affordable launches, right? So there are monetary issues with launches, having connections to get a launch. There was a lack of commercialization previously. Obvious technical deficit. It's hard enough to build a satellite, but now you want to build the rocket too and launch it. Lot of issues there. Right now, the price, more or less, off the SpaceX website is $1,400 a pound to launch something into space. I don't think I could afford to launch 1 pound. Still. Spacecraft buses. Not a literal school bus, spacecraft bus, right? These are the actual components you use to assemble a spacecraft. Everything used to be built in-house, assembled in-house. You might have to farm something out to somebody with some specialized knowledge for your power supply. You can just buy these off the shelf now. There are companies that will sell you. If you need an attitude control box for a spacecraft, they'll be like, yeah, I'll sell you one. Here's the interfaces. Here's the text. Somebody else will sell you a star tracker, instruments, all the way down to instrumentation you can get, and just assemble that. Some of these are a one-stop shop. Another issue we had was communications. We talked about our cable. We talked about building a rocket. We talked about building a spacecraft. You had to have something to talk to the spacecraft, right? So this was very expensive. These were the barriers to space. These are really no longer the barriers. What barriers? This is from ANSYS Systems Toolkit. They have a really cool simulation platform where they can plot things, and this graph shows you more or less kind of recently everything that's in orbit around Earth being tracked right now by like NORAD. I believe, I'm probably going to get this wrong, I think the green dots are satellites and the red dots are debris. And so there's a lot of stuff up there, so obviously that barrier is not really existent anymore. And then a little sidebar where there was a rapid unscheduled disassembly of a recent Boeing satellite, and so now there's even more pieces up there, right? So space junk begets more space junk, unfortunately, unless it burns up. We talked about what's up there now. Let's talk about the ground systems. Has anybody heard of KSAT? Anybody familiar with KSAT? We've got a couple hands. Commercial ground system. You go to them, you say, I have a satellite, this is what it speaks, this is the frequency, and they say, that's cool, we can have you up and running in 24 hours if you want. That's an emergency situation, but they've done similar things. Worldwide access ground station. And that's just one provider. Everybody knows AWS, right? AWS worldwide access as well. So these barriers are rapidly dissolving, essentially. In a not-so-parallel universe, anybody work industrial control, IoT devices, or have these things at home? Probably IoT. You probably don't have industrial control devices at home. You might. I'm not here to judge. So what happened with ICS and SCADA systems, right? They assumed they would be air-gapped forever. Nothing would ever plug into their network. Nothing bad would happen. These facilities, they weren't even really secure facilities, some of them. They just said, well, you know, the Ethernet's on that side of the wall and the important stuff's in here. Nothing bad's ever going to happen. Stuxnet, good example, right? Iranian enrichment facility, air-gapped, multiple levels of defense, and the writers of Stuxnet basically said, here's what we're going to do. We're going to look for a very specific industrial controller hooked to a computer. And if we don't see it, we're just going to replicate on every single device we can find and just hope for the best. and it worked, right? Eventually it got there. I'm not sure how long it was out there before it got to the centrifuges in Iran, but it made it happen, and that was air gapped. You know, a friend of a friend picked up a hard drive or a USB and plugged it in, and so on and so forth. So that's happened to ICS. ICS is aware of this. Internet of Things, grandma's probably not updating her smart fridge at home. I don't know if grandma has a smart fridge, but you know, there's a whole nother host of devices. So we are starting to see similar issues in space related and spacecraft. So obviously we've got a problem here. Previously, ground stations were pretty linear, all right? If you're a government agency or the military and you had the need to launch a satellite, you built everything. You built the Mission Operations Center here. A mile down the road, you built a satellite dish, you hooked them together, you launched your satellite, and you owned the pipeline. It was siloed. A lot of air gapping, not a lot of sharing of things, equipment, and people. And generally, kind of like the early days of the internet, it was just kind of assumed if you're plugged into the switch, you're meant to be here. Do what you will with the satellite, right? It was not or is not meant originally to be integrated. We're seeing this change. This is a big change. Not only web partners, you've got everything's getting complicated, people working across larger geographical areas. You have a mission operations center, backup mission operations center, a test network, a development network where the software is written, science instrument partners across the world, they need their data, security operations center, infrastructure, backup infrastructure, and your satellite. And now it's even increasingly more common that this goes through, the cloud at some portion of these hops. So now we're starting to run into issues. Not only are we connecting more things, there's more things up there that can listen to your communications if you're not using security protocols on a satellite. So we kind of covered a little bit of background about sort of the problem and how this has evolved. Let's take a little bit of comparison of satellite networking and traditional networking. We have to get four acronyms to do this though, right? Has anybody heard of CCSDS? All right, like 2 people. Consultative Committee for Space Data Systems. It's like 28 member nations. These people get together and they create standards and protocols that are optional for people to use, but they solve a lot of problems, so they're gaining a lot of steam, a lot of traction. Like I said, engineers from 28 nations. They have released standards for telecommand. So anytime I say command, I mean to a spacecraft, and telemetry from a spacecraft to the ground. They built upon this and added a space data link security protocol. So if we look at a very simplified kind of network stack OSI layers, at the bottom you've got your media. For traditional IP, we're thinking Ethernet, copper wire, maybe fiber. At the data link layer, still bits and frames. Really the big difference with, I'd say the biggest difference kind of in the stack idea is that there's a synchronization and channel coding sublayer. All that is additional extra headers for radios to actually resolve the bits and bytes and make sure they're interpreting the transmissions correctly. Once you have those frames, very synonymous to Ethernet frames and telecommand frames, you have your packets and data, your upper layer, your applications that run on top of that. So what is CryptoLib? This has been 20 slides, and now I'm telling you what CryptoLib is, right? Because there's a lot of background. CryptoLib is an open source attempt, a pretty good attempt, might I add, of the Space Data Link Systems Protocol and the extended procedures. The original implementation of this was written at NASA IV&V, which if you haven't heard of NASA IV&V, it's in Fairmont, West Virginia. It's one building in Fairmont. The goal of CryptoLib is to encrypt and decrypt CCSDS transfer frames, telecommand, telemetry, and AOS. Long story short, command and telemetry. It's open sourced, C-based, uses libgcrypt under the hood. We've also added support for Wolf SSL and JPL's key management and cryptography solution, which utilizes Bouncy Castle on the back end. Okay, what CryptoLib? Now, why CryptoLib? Why is CryptoLib? NASA IV&V has a lot of experience with CubeSats. If you've never heard of a CubeSat, it's a very small form factor of satellite. As far as satellites and expensive things go, they're considered disposable. Okay? So we're talking like a loaf of bread is a standard CubeSat. A cube is defined as 10 centimeters on every face, so more or less 4 inches across each face. And these are usually in 3s, which is about a loaf of bread, 6s, 2 loaves of bread, and so on and so forth. And there are some requirements that we're going to talk about that have been levied on missions. The CubeSats are not exempt from. Another reason we chose CryptoLib to work on is the CCSDS protocols are already in use. We use them internally on some software. They provide additional standards on how to encrypt only or authenticate only or do both. We also have the issue of unencrypted command links. What happens if somebody adopts a protocol, right? If I make a mission and I'm using an open source protocol that I'm following and it's all open source software and you want to clone and own that, what's the first thing you do? It's probably not change the command dictionary to be unique. There's probably some overlap there, right? So unfortunately, scientists want to share all their data and the military much rather would not. But they use some of the same operating systems or same concepts. So we want to look at securing these links because a lot of these basic dictionaries are out there. We're going to talk about some flight software that's open source after a while as well. We want to remove all the magic from having encryption. There's no PhD required, however, somebody needs to know a little bit about what they're doing. We're not writing these protocols from scratch, obviously. I'm not writing my own encryption protocol or decryption. We're just implementing the algorithms on top of the data format that exists. So worry not. If you think you want to do that, you should probably think again. I'm not going to stop you. But it is open source, so it's there's no black box. We're getting more and more following online. It's transparent handling of the process, no vendor lock-in. We wanted to save money. The government, the military, the government at large is happy to just reinvent the wheel sometimes. Or this team over here has developed a piece of software and this team over here that doesn't know about the first team writes their own version and you have all these versions that do the same thing. We're trying to eliminate some of that with the cryptography, at least for basic missions. And then, sidebar, the GitHub's really easy, /CryptoLib there. But NASA standard 1006A is another reason CryptoLib had to exist. And basically NASA realized we need to start encrypting these links to satellites, right? There's a space policy directive that came out. And it says, programs or projects shall, we must, protect the command stack with encryption that meets or exceeds FIPS 140. Deep space missions may choose to limit controls applied to the space link. So if you think about how long it takes hours, right, on some of these deep space missions to get data back and forth, they may choose to limit controls applied to the space link if certain controls pose significant burden in operability or mission success, and the threat is low. And then category C, class C or D, which is usually CubeSats, tech demo missions, they may authenticate without encryption if they have no propulsion. So even if you have a tiny CubeSat with a tiny amount of propulsion, you're going to have to encrypt, all right? And that's interesting because that's expensive. You can't just bolt this stuff on the CubeSats. They're already small, like we talk about. And they are not handing out waivers hardly at all for some of this. So we'll talk a little bit more about security types. CryptoLib gives you several options. There is, of course, a debug plain text, because if you've ever written code and tried to analyze the encrypted output, that's not really useful for unit testing sometimes. So you wouldn't use that on Orbit, but there is a plain text. Authentication only, so basically you run it through an authentication algorithm and attach a MAC at the end, an authentication code. You can do encryption only of the data, not the headers. Or you can do authenticated encryption, which encrypts the payload and then still adds a MAC at the end. If you've ever seen Independence Day, Jeff Goldblum, very smart man. It's a cable guy in this movie. He's got a little magic device he puts on top of his car. He can triangulate people in the White House. But the whole thing is the sort of the background, spoiler alert, it came out in 96. If you haven't seen it now, you're probably not going to. Aliens using their own satellites against us, right? And they had an encrypted message that somehow Jeff Goldblum managed to crack, but good for him. Maybe they were using CryptoLib. But back on topic. So, why CryptoLib? Swap C. If you've never heard of Swap C, it is basically a three-sided triangle for mission design and overall requirements. Size, weight, and power. Those are your three biggest constraints outside of money, which runs everything, right? That should be a dollar bill in the middle. So if you increase one of these things, you're probably going to decrease or significantly impact the others. So for a CubeSat mission like we talked about, it is cheaper. Studies have shown that it is cheaper to incorporate security at the outset. Bake it in instead of trying to bolt it on at the end. You don't want to do all your testing and then try to bolt the software for crypto on at the end. That's hard enough as it is. It's even harder if you're going to think you're going to mount a hardware box to a CubeSat because of your size, weight, and power constraints. And vendors would love to sell you a crypto box anyways, but it's still going to be really expensive. So these are all driving motivation factors for why CryptoLib exists. But what we're doing is at a very high level. We have an unencrypted command. It goes through CryptoLib, does some magic. An encrypted command comes out. You send that to the spacecraft. Spacecraft receives it, decrypts it through CryptoLib, and then it acts on that command. That's the goal. That's the flow. There are a couple deployments that support this. I'm a big fan personally of the standalone deployment. Basically, it's a box that just sits in the middle of your network architecture. Your ground station connects to CryptoLib, and CryptoLib is configured so that it basically accepts the command, does the encryption, and spits it out on down the line. I like that personally, especially for development work. Once it goes over the air or whatever to the spacecraft, it goes to the command ingest, it gets processed, goes out onto the spacecraft bus so the spacecraft can actually act on that command, and then the reverse happens if you have it configured to do so on the downlink. Downlinks per NASA standard 1006 do not have to be authenticated, but your commands at least have to be authenticated. There is a second deployment option. This is Jet Propulsion Labs. We work very closely with them. They have a key management and cryptography solution. It is enterprise software, basically. It's CryptoLib Enterprise on steroids with like all the extra access controls and logging and integrated into their larger suite called AMOS, which is the Advanced Multi-Mission Operations Systems Toolkit. And it's got a whole bunch of stuff with it. But we worked very closely with them to provide CryptoLib for their missions. And they have used CryptoLib for compatibility testing, if not on orbit. I just don't want to say that and be wrong. With Lunar Sunrise and Lunar Trailblazer. So with their own implementations, they've added this already. So now we're really getting into the good stuff, right? We got about 9 slides left here, and now we're getting into like, tell me the technical stuff, spaceman. I don't know what we're talking about yet. So what do these layers look like? A space packet, it's like an IP packet. It's got a header, and it's got data. Pretty straightforward. It's a packet, it's got the word space in front of it, so it's cooler. A telecommand transfer frame, a frame that goes up to a spacecraft. It's got a header, it's got data, and trailer. If you put the space packet, spoiler alert, inside the telecommand frame, you have a telecommand header, space packets in that data frame in the middle of it, and then you have your trailer. This is all highly configurable with links and everything, but that's outside the scope. So the goal is to take a full transfer frame, encrypt the data that's in the middle, hopefully correctly, right? So when you decrypt it, you get the same output, and be able to reverse this on the spacecraft. So, really simplified example, we have an unencrypted frame at the top. It has a telecommand header, it's got space packets, plural, some in number in the middle, and a trailer. This packet, the way CryptoLib is working, this whole frame is fully formed and ready to be encrypted. When we pass it to CryptoLib, you'll notice that CryptoLib is actually adding more headers and trailers. So we have to be very mindful of maximum overall length and do a lot of math to make sure that all checks out. But basically, we encrypt the data in the middle, Now we have to add a security header and a security trailer, and then that's ready to go to the spacecraft. So that's sort of the process of what we're doing. We have to obviously add more headers to make this work. A little more technical look at what happens here. At the top, this is a TC transfer frame. It's a little small, but I'll walk you through it. You have a transfer frame primary header that's 5 bytes long. You have a data field, and then your trailer, which is just a FECF. It's basically like a CRC, more or less. You call CryptoLib encrypt, you end up at the bottom. This is just a little like closer in-depth look at where, you know, the green are the new security headers, the red is your encrypted data, and there's a segment header we're adding depending on if we're breaking things up and we need to break this up into bigger or smaller chunks. And this all comes from CCSDS document 232. That's cool, but like, what are we doing? We're working on it, right? We're doing some stuff. This is an active development. So spoiler alert, if you look at this at GitHub right now, you'll probably be like, I see problems with this. Shouldn't be a lot. We've got a really good team working on it. And it's actually grown, I think, a little quicker than we expected. The baseline implementation is around 99% done. So more or less you could clone this, and we talk about barriers to entry, and I'm just kind of like fomenting this thought while I'm talking aloud here, right? Okay, so now we have cryptography, and now we've also simultaneously removed the barrier if you know what you're doing, but that would require you to have the correct encryption keys, right? That's the benefit of cryptography. Doesn't matter if you can listen in on it if you don't have the keys. But anyways, the baseline implementation is about 99% done. The code has been refactored. We wanted to reduce the complexity of code. The initial pass was very linear, and I wrote it in like super long blocks when I kind of rewrote the beta version. And it was very linear how it did it. The problem was my functions were stupid long. And a code scanner was like, this is too complicated. There's too many forks in here. I'm like, that's fair. So we took the team and we broken it up to get easier testing of the methods. And we want to increase that unit test coverage to 100%. Some missions are planning on using this, and their mission class will dictate that any code that flies with them, and this is considered mission critical, obviously, would have to have 100% unit test coverage. So more work for us. Really cool. Somebody's going to use it sooner rather than later, but now we have to rewrite a bunch of stuff. We're also actively working on the extended procedures, which adds all the kind of like, you're probably, if you have any crypto background, you're probably thinking a little bit about like, how do we get keys up there? Do we just preload these keys? In old missions, they would just be like, you've got 300 keys, man, make it work. Like, don't lose them, because these 300 keys on the ground or the 300 on the bird, they have to last the mission, you know, the mission life cycle, lifetime. Don't mess up, don't leak them, don't lose them. Don't reset and not know what key you're using. So extended procedures is in process, and we actually have a lot of it done. It's more of just unit testing and finding partners to test with against any other implementations, which there really aren't. This is like outside of vendors that want to sell you a box that is allegedly compliant. There aren't a lot of implementations of this. This is about the only one that I'm aware of, if not the only. But that gives you key lifecycle management. You can stage keys, activate keys, deactivate keys, things like that. You can change between security associations, which is too in the weeds for this talk, but the gist of a security association is which key works with which channel and what kinds of encryption am I doing. Am I doing AES GCM? Am I just doing authentication? Which algorithm am I using? And things like over-the-air rekeying and so on and so forth. So that's the extended procedures we are working on. One of the cool things about CryptoLib is we designed this to work on flight and ground. Basically, you just cross-compile it. So we wanted to be able to use the same library, same code base, same core functionality, obviously with different wrappers because there are different headers for telemetry and commands. So now we could talk about the spacecraft side a little bit. Anybody in here have experience with spacecraft flight software? Cool, awesome. This is the right place then. All right, so NASA has an open source fork of what they call core flight software, CFS. This has been around a really long time. It has a lot of really cool heritage. A lot of missions have used it. It works on the concept of apps that hang off of a bus. CFS provides core apps that, spoiler alert, provide the core functionality, and additional apps that exist outside the core and give you some expanded baseline functionality. You as a mission will have to develop some of your own apps to actually interface with your devices and the protocols and whatever sensors you're using. And then these apps pass data on a pub/sub message architecture. The gist of it is we have the CFS lollipop diagram, they call it, straight off CFS website. The apps in green are the core functionality apps. They make up basically the framework that everything else uses. And the font's a little small, but you have your software bus for message routing, time services, everything needs to be time stamped. You have executive services for starting and stopping other apps, event services for logging and error messages, and table services for being able to load, make modifications on the fly if you need to, and reload stuff on orbit. So a pretty robust core. The apps in blue are actually standard CFS applications that they offer and do some like pretty cool baseline expanded functionality. You can store commands, so you can do relative time sequences or absolute time sequences if you want to upload command chains. There's a scheduling app that basically dictates how fast things on the spacecraft happen. Limit checker, which if you love digital logic, limit checking is basically like fault detection and correction, digital logic and kernel maps on steroids. So it's pretty cool. Memory manager, CFTP, so there is a higher level app for file transfer that can do reliable file transfers, not just basically UDP-esque fire and forget and hope the spacecraft has it. And then there's data storage. So how do we actually like grab the data off the bus, store it in the meaningful files, and then transfer it later? So that's kind of the CFS baseline. You as a mission will probably have to develop the yellow bubbles, of which there are versions of some of these out there. So command ingest gets commands into the spacecraft, telemetry output gets the telemetry down to the ground. But if you have anything that uses SpaceWire or you need to interact with any sort of sensor, you probably have to write a custom app. So star trackers, attitude detection and control, instrumentation, magnetorquers, inertial measurement units, GPS, any of that stuff, you're going to have to create an app. It's not that hard, it just sounds kind of scary. CFS does have some really cool heritage. Most recently it was used on some of the instrument simulators for James Webb. I might be wrong on this, but I believe CFS is the backup flight software for space or SLS, Space Launch System. I think it's the backup. Like, so after if the primaries go down, you're riding on like 40-year-old government software, the best of the best, baby, all right? But like, it's got good heritage, right? So, I mean, it really is tested. And it has a lot of use through Goddard. Goddard Space Flight Center uses it, maintains it, development. It's an active development. There's a lot of stuff here. There's been a lot of background to get us to this point to talk about the problem, right? We've talked about SpaceLink background. We've talked about encryption. We've kind of defined what that encryption looks like, the issues with access, and then we pivoted up and talked about the spacecraft side and flight software. So there's a lot going on. And if you have interest in this and your thought is, this is really cool, I don't know where to start, this is where you want to start. GitHub.com, NASA/NOS3. We call it NOS Cubed. NOS Cubed is the NASA Operational Simulator for Small Satellites. It is a satellite in a box. You can download it and deploy it through VirtualBox. I don't maintain this directly. I help a little bit, but like I'm not like the driving architect. I think the most recent versions are, actually I think I did pull main the other day. It's like you just download a file and run it, and like it's a whole bunch of Docker things and everything spins up, but it's really cool. And it has CryptoLib integrated into it at the baseline. In this example here, this is actually, again, I know we really can't see it, but this is like a full encryption frame. But in the top left, we actually have CryptoLib running. It's showing you what it's receiving and spitting out. We have flight software. We have a ground system integrated for command sending. We use 42, which is an open source tool developed at Goddard. It is a dynamic and attitude simulator. So you have a spacecraft that you can tell it to do things and it'll flip around in space. All right, so it's pretty cool. This is essentially the end of the show. I'm not really going to do what I would consider a great live demo. How about a staged one? Just cause. Oh no, I gotta share. Let me. Will the government allow it? Nothing like having key sharing issues in front of a whole bunch of tech people. There we go. Let's see if we can duplicate. Boom. Awesome. All right, so this is NOSCube. This is downloaded. Obviously, you can see that my poor little laptop CPU is, or at least the NOSCube CPU is kind of pegged at the moment. Let's see if it actually comes out of sleep very well. So we'll send a no-op command. Cool, awesome, it's alive. So in the top right, we have Cosmos, which is a ground system. The older versions of it are open source. They still maintain an open source version, but if you want to access some of the cool newer features, it's licensed. It's one of those things, they got good enough that they're like, we want to be paid for it, which I don't blame them. So what we've done is if we go through the command sender and I click send command, this goes through the ground system, through CryptoLib. We see CryptoLib what's the word I'm looking for? Advancing here. This is not encrypting right now. This is in plain text mode. It's just adding security headers to the space packets. It can do it. I don't have it configured, and I didn't feel like rewriting the security associations before this. Then it's received by flight software in the bottom left, which acknowledges our no operation command. Meanwhile, we've got a little CubeSat here in the viewer. It's just kind of tumbling. This is approximately an estimation of a 3U CubeSat, so about the size of a loaf of bread. And then we have 42, which I'm not running this really fast right now, that's actually doing the attitude dynamics, and that little dot somewhere around, I don't know, what is that? India, Europe, over that way. It's that's the satellite as it's actually moving through its orbit. So we're actually doing the orbit, getting that information, passing that into the satellite. The reason this is cool with NOSCube is NOSCube has hardware simulators built into it. So I'm not going to go entirely into this, but you know, even the power system in this version, based off of the sunlight and where you are and how the power system is set, it is actually updating the charging rate of the batteries based off the angle to the sun. So we've done a lot of simulation that we've just released for free for the hardware, so the apps can actually be like, so the power system app can say, hey batteries, how much battery is left? And battery says, I'm at 89%. And so flight software can use that to test fault detection and correction, spacecraft recovery modes, and all that stuff that's really hard to test on the ground. You can break things with this in ways that you can't do with hardware, and that really adds to the value of testing. Nope, not going to connect to the Wi-Fi, never mind. We actually, just a little more credence on this and about how this ties CryptoLib together. We actually developed a small sat at NASA IVNV. I was an intern there for that project, called STF-1, Simulation 2 Flight 1. And NOSCube is the baby, the whole driving factor. We actually use NOSCube for spacecraft development and more or less froze code development before we had all the hardware integrated, because we wrote the simulators. We took the documents, we wrote an entire virtual spacecraft, made the sims, mocked it up, wrote all of our fault detection and correction code, wrote all of the interfaces, and we said, okay, it's cool, now we just need the hardware. And it had a successful mission for 4 or 5 years until it finally made re-entry. So it's kind of proven itself, at least in one case. With that, that's all I got. Any questions? Cool. Yes, sir, go ahead. Yeah, I think I read something about that. Yeah.
What is their involvement? What is some of the commercial space involvement with property like that? They obviously still have to enforce this 140 encryption.
So that's a government directive. I don't know that they have to. I know it's government like levied on missions that are government funded. If you're a private entity, you probably have a little bit of leeway with that. What some of these places are doing though is they're buying basically like a matchbox or like a FIPS tunnel essentially. So it doesn't really offer the same level of granularity that CryptoLib does. It's basically just, you think of like an IP tunnel, right? Data goes in and it's received. The benefit with CryptoLib comparatively is that I can actually take all the data and break out the different streams, and I can give you your decryption key for your science data, and we can keep it decrypted to you. Yeah, yeah. So, yeah, you're welcome. Anything else? Sure. How much logging data? That's a really good question. So, one of the problems with like things in space, right, is like rad tolerance, right? Radiation is going to mess up stuff. So your non-volatile storage is very expensive. So it depends is the short answer, which nobody likes. But it's up to the missions. So I have seen mission operations where their sort of flow is that they store their data in very granular files sometimes. Like this is my instrument data. This is a list of commands that I've operated on. This is everything else, right? And it's a huge file. And then like once a week, they're like, anything bad happened? No? All right, we're going to delete that big file. So they manage it kind of like that. It varies, but it all depends on your downlinks too. If you're in a low Earth orbit, and you're using, you know, if I can use sort of what I know about some of the government examples, you're sharing a satellite dish with somebody else, right? At one point for STF-1, we were sharing with 6 or 7 other CubeSats on one satellite dish in Wallops. And they were scheduling, they're like, you get 2 passes today and none tomorrow. And we're like, okay, well, we're going to do the best we can, right? So it all comes down to how fast you can get data down as well. And missions will tailor that. If they know they can expect 2 7-minute passes a day on average, they will pare down what they would like to store. And they usually prioritize science data. Housekeeping kind of gets the boot in terms of what has good storage. So. I'd say it depends, honestly. That's not a terrible thought, right? Theoretically, your radio should drop anything. Like, it would be cool to just have a counter. Like, the simplest way is have a counter of bad frames or something that's been dropped, so you're not storing those. But at some level, you want to have that ability, basically forensically, right? Be like, okay, I want to have a file that takes any bad command. I'll store the last 20. That way you cap it, right? And then you'll just refresh that file once it's full. So it's not great. It's not the best logging, you know, but you're at a premium for space and storage. So cool. Anything else? What do you want?
Is there anything like a satellite or space-based CPM?
Yes, there is actually. So aerospace does Hackasat, and it's close to hacky sack, right? Hackasat, and it is exactly that. They take I don't know where they are right now on as far as like cycles, but what they were doing was preliminary teams. If you passed their like early challenges, then they like give the top 10 teams or something access to a live satellite that was nerfed, obviously, right? They're not going to let you spin around and fire the lasers, but and I think they actually had people successfully do that. And so those mechanisms look different, right? Depending on what's going on. And obviously it's real, but it's semi-contrived, right? Whether that was a key leak or a bad actor had data or keys or whatever that is. Spoiler alert, I wrote a sim a few years ago. I can't really say I wrote a sim. That really kind of oversells it. I integrated a sim a few years ago, one of the first projects I did. And they used that to train the Hackasat operators for the first the first hack is at. That's how they use and train the aerospace guys. So like, here's a sim. It's a spacecraft in a box, and this is like what you have access to and how it works. So there are a lot of uses for things like NOSCube in terms of operator training, cybersecurity. You can drop that into a larger network architecture. Like if you're spooling up like a big like red team, blue team, capture the flag, attack and defend, you can be like, that's cool, here's your crown jewel. This is a mock, it has paths and routes to here. This is my ground station that does my end crypto, and here's my spacecraft. What can you find at which hop? So, good question from my brother, who's definitely not a plant in the audience. I didn't actually ask him to do that, so. All right, cool, I think that wraps it up. Thanks everybody, appreciate it.
See you then.